Okay, time to start. There are 3 students present out of what is left of 62, which is how many percent? Like 5%, right? Let's see, so the live stream is up and running. For those who are watching at home, that would be another 59 students. Okay, and we continue where we started, where we ended last time, and that was in basically chapter 4 of the lecture, systems of equations. And by now, you should be able to enter symbols with SymPy in Python, form a set of equations that you connect to each other if you have more than one variable, and find the solution of this system of equations of multiple variables if the system has solutions. And I showed you last time how to check if a system has a solution or not. We discussed the example of a 2x2 matrix and showed that if the determinant is 0, then the system has no solutions because we cannot find the inverse of a matrix. We also discussed numerical stability of our algorithm, or of problems that are represented through a coefficient matrix A. We introduced the condition number as the norm of the matrix A times the inverse of the matrix A, and said when the condition number is very, very large, then most likely we have some issues finding the accurate solution numerically. But if the condition number is small, like ideally it's 1, 7 is okay, 10 is okay, probably 20 is okay, then that is also okay. And as an example, we looked into a comparison between the symbolic exact solution and the numerical solution that we plotted over a parameter p, which scans through different values of the condition number. So here in the plot of the left, the plot to the left, we plot p over the error in our solution, right? Where a p-value of 1 gives us the largest errors, and we compare this to the p-value over the condition number of our 2x2 matrix, and we see that yes, the condition number spikes at p equal 1, but is rather low at smaller or larger values of p. So far, so good? Okay, and then one more time, what is important to me is our first bit of the real numerical analysis of an algorithm that you see here. Right, so in this block, we do the proper analysis of, okay, what do we actually expect and what do we introduce here at the end? That is the definition of the condition number through an analysis of small changes. Right? And if you really study numerics, then algorithms you would more deeply analyze through the impact of small changes on the accuracy or speed of your result within that algorithm. Scaling laws is another one, but this here is not an introduction to numerics. This is an introduction to scientific computing, right? So we introduce bits and pieces, so you can do some computation, and here a little bit extension into the numerical field. Okay, there are 4 students now. Very good. It's okay. Well, you can always join at home. You can always join here. Shall we actually check how many students join at home? So there are 3 people who watch. I see you are watching, right? No? Are you watching as well? No? Are you watching? So 2 watching. So there's 1 guy at home watching as well. Okay. No worries. It's okay. You can watch later as well. Mm-hmm. I mean, you did that all in front of the midterm, right? Where I saw the spike in the activity on YouTube. You learn whenever you feel like learning. It's okay. I understand, but I have to be here on fixed timings, right? That's what my job is. Good. So, what else shall we do next? Right. So, linear systems and SciPy. So next we're going to use SciPy to use systems of linear equations, which is here are abbreviated with linear systems. Let me just get a hang of the zoom in a little bit, so you can watch it on your phone very nicely, right? 5 students, very good. We should make a statistic, like what is the arrival time over. It would be a nice investigation. Did you actually know that there's a statistic analyzing the head height of students sitting on their seats over lecture time? And when the lecture time starts, you're all sitting like this, right? And then over time, you all slide down until like 5 to 10 minutes in front before the end, and then you sit up again, right? It's not only like you guys, right? It's like other people investigated this actually. There's a real study about that. Okay, so I was told. Okay, so now we use SciPy. SciPy is our scientific Python module. The question is, why should we use SciPy to solve systems of linear equation? Just now we used Python, NumPy, as well as SymPy. Don't we have everything we need? Well, it turns out that there are more than one way, or there is more than one way to solve equations. And as I mentioned already, there are algorithms behind our solutions that we use that other people implemented. Our example with, was it x square equal tangent hyperbolicus x? That equation we couldn't solve because nobody implemented a solution algorithm, right? So if there are more than one way to solve problems, how do we know which one is the best? Well, we could benchmark different approaches. The other way is, do we look for accuracy? Do we look for speed? Do we look for memory? Don't be shy. Don't be shy. Or we look for, what was it? Accuracy, speed, or memory efficiency. And then depending on which restrictions we have, one could make different assumptions and then design an algorithm, particularly for this purpose. Okay, so before I start talking too much about computer architectures and different types of computing, let's go back to the main part of the lecture. Now we introduce SciPy, and in particular, we look at the LU decomposition. So when I ask you what is the LU decomposition, then I want to know from you that, oh, this is the lower and upper triangular matrix composition. So what is the idea behind the decomposition? The idea is when I take one matrix and I have another matrix, and these two matrices are, for example, to make it easy, square matrices. I take the product, I get another square matrix, right? Now the idea is, maybe I have a problem given in matrix form, and I can find the product out of two matrices that represents the same matrix I started with. And if I do very, very smart choices, these matrices come in triangular form. Do you know why it is good to work with matrices in triangular forms, or do you know what are triangular matrices? Any idea? Do you recall? What's a triangular matrix? Yes, no, maybe? Anybody knows? 1, 2, 3, 4, 5, 6, 7 students. Anybody knows what's a triangular matrix? You know what's a triangle, right? You know what's a matrix? You know what's a diagonal matrix? Just the diagonal, right? And the upper triangular matrix is you take this diagonal and everything above this diagonal you put values. Everything below you put zeros. It's the upper triangular matrix. And the lower triangular matrix is you take this diagonal and everything everything above becomes zero, everything below becomes with values. How about the diagonal itself? Diagonals also can have values. Okay, good. So here is now an example, right? So what do we have is 2, 3, 5, 4. That is matrix A. And I can take the pointer here, right? So matrix A equal 2, 3, 5, 4. And I can represent this matrix as 0 0.4, 1, 1, 5, as a product with 5, 4, 0, 1.4. Okay, so does that make sense? Let's try it out, right? How do I do this? Insert below. So when you see something and then, can you do this in your head? This matrix multiplication, can you confirm it's correct or not? A little bit difficult, right? So what we do, we import. It's a little bit funny here. My laptop is not working properly. What is going on? I don't want to print. Thank you. I put. No, my keyboard is not working. That's very weird. What do you do when your keyboard is not working? You restart, right? Is anything happening here? No. What could it be? What could it be? How about I close this and I go here again. And if this doesn't work, I need to restart. Right. A bit funny. My keyboard is set English keyboard, yes. And so what you can do in the meantime is open NumPy, plug in two matrices, and do the matrix multiplication to see if you get the result. So nothing seems to work here anymore. It's game over here. Nope. So I will need to restart and then